Okay, here we are for the new Continual AI seminar session, and today we have the pleasure to host Tim S. And Tim will talk about his recent paper titled A Procedural Word Generation Framework for Systematic Evaluation of Continual Learning. Tim comes from Goethe University, and the paper has been accepted recently at the NeurIPS benchmark and dataset track. So if I'm not mistaken, Tim will talk about how to use generative models to build more principled continual learning benchmarks and even more robust evaluation protocols. So I'm looking forward to the talk. It seems really interesting. So please, Tim, the stage is yours.
Yeah, so thank you for the very nice introduction. You took basically everything away from me that I wanted to say on the slide. Maybe this one addition. This is a joint work with Martin Mund, Julia Pirsch, and Viswanath Ramesh, whose images you can see on the slide. So let's go into the presentation. In the beginning, just so that you kind of get a feeling for what's awaiting you, I will first talk a little bit about the background of this work, which is, of course, in continual learning, but more so in the benchmark area. So I'll talk a little bit more about this there. Then we're going to see, then I'm going to bridge to the endless continual learning simulator that I'm going to present you. And finally, I'm going to talk about the initial experimentation that we did in the paper on the basis of this new benchmark from the simulator. And I will talk a little bit about prospects of future uses of the simulator and future work that we'd love to see. So let's begin with the background on continual learning, but more on its benchmarks. So when talking about continual learning, currently, especially for neural networks, this can be very nuanced, but what we try to generally achieve is that when we have a neural network that has been trained on some kind of initial information, then we want to be able to add new information or incorporate novel information into this trained model during its lifespan. And we would like to do this without having to reiterate all of this previous information that we already fed into the network, but we wanted to only look at the novel information. Now, if we do this with our day-to-day neural networks, so to say, we will encounter what we call catastrophic forgetting. And I've quickly sketched up what this will look like in your analytics tool. As you can see, for the novel information, everything is fine. Our model will pick up on the information and our test error is going down beautifully. But at the same time, if we look at our previous information, the test error will go up drastically and fast, eventually up to a point where it's like we have never fed this information to our network or to our model at all. And we can repeat this process if we have even more novel information that we show in isolation. Our model will keep forgetting all its previous knowledge. And this is basically due to the training process that we employ to train these neural networks. And this will lead to greedily overwriting the representations for the initial or the older information by representations for the novel information, and this will happen greedily. So as continual learning researchers, we try to find mechanisms to circumvent catastrophic forgetting or even to finally overcome it. And to test our new methods that we developed, we need some kind of benchmarks to do this. Now, one of the problems is that there are not many continual learning benchmarks, and by that I mean that they are explicitly designed for continual learning. What happens most of the time is that we, especially in computer vision, is that we reach back and take data sources, for example, from image classification datasets. But because these do not inherently incorporate a continual learning challenge where we have the sequentialization of our information that's coming in, we kind of need to superimpose it ourselves. And this is typically done by some kind of augmentation, such we split this data set into individual subsets. And one very common approach to do this is to split it along class boundaries that are naturally incorporated into our original data set. So here we see one example for this. This is the SplitCIFAR or SplitCIFAR dataset that has come out of the CIFAR dataset basically. And we did this by first showing the network only dogs and cats, then only cars and trucks, and then more classes until maybe finally planes and ships. And then our model should be able to classify all of these categories. And yeah, it should do fine. And we could test it against a standard neural network that had access to all of this data at once. Now, from our perspective, when we started this work, there were a few open aspects to this. And I will now talk about, they're kind of all related to the same issue, or they lead to the same issue, but they have different angles, and I'll now explain a little bit more about this. So when you look at this structure of benchmarks, the first thing that you will notice is that the shift that we experience in our data distribution means the shift between two tasks. Here, from, for example, from dog to car, this is quite the abrupt shift. But if we want to look at more gradually changing distributions, then we have a problem, because most of the time we cannot actually do this with this kind of benchmarks. Now, unfortunately, such gradual shifts are most of the time default if you look at real-world applications. Our day-to-day world is changing rather gradually instead of you having this abrupt borders. And then another thing is if you want to incorporate online learning or temporal consistent data, which is really close to, if not a subpart of continual learning, then again you will have a problem, because you cannot, there is no data basically available and you cannot really evaluate this. The same is true if you want to go beyond image patches, for example, for other annotation tasks such as semantic segmentation or some other annotation task, basically, yes. So then another angle to this is that the original data sources, which here, for example, was the CIFAR dataset, they were designed with a whole different purpose in mind. They were not designed for continual learning, but they were designed to show the generalization capabilities of neural networks. So, of course, you have this class categories of dog, and there are only real images of dog in there, but you're not quite sure about all the things that play into your data distribution. And now with catastrophic forgetting, which especially emerges from this distribution shifts, when we evaluate continual learning, we would like to be sure about what are the actual shifts that we're facing. And these insights may be limited if we only consider, okay, we had the shift from dog to car, but there may be more happening in the background. And then the last thing to consider is that this split along classes is, of course, only one example that you can do, but this is quite a common example. And if you look through recent research, this is the, again, kind of default approach that is taken. And more and more, one may get the feeling that we have the situation where overcoming catastrophic forgetting is kind of set equal to being able to learn these classes in a sequence. And even though we inherently know this is not necessarily true, we see more and more how these assumptions on this particular task in this particular benchmark setup are influencing the methods or the approaches that we see towards continual learning. And one example that I want to pick up here is, for example, multi-headed architectures, which means we have one model, but then for each task we have a different output in our from our network. And yeah, this is something that shows really great performance on incremental class learning tasks. However, you have to ask the question whether this is a good approach towards, for example, gradually changing distributions, and how you would apply this mechanism then in the same way. And again, this is only one example. If you look through the research, you will see there and again some details that tell you, okay, this was designed for this task in particular. So with all that, what I actually want to say is that we would love to see more realistic evaluation in more varied scenarios of continual learning. And by that, we basically mean going beyond only evaluating continual learning on scenarios of incremental class learning. And we realized that this is, to a large part, a problem of available data. And acquiring this data in the real world is actually a tedious and a complicated process. So we turned towards synthetic data for this approach. Now, our main contribution is basically our benchmark generator or dataset generator. And this is a computer graphics-based simulation framework that procedurally generates an endless world. And this endless world has a stochastic sampling process lying below it. And this process is parameterized. And this parameterization you can change at runtime. So we can place a camera in this world, and we can create highly customizable video streams. And by this, we mean that we can, because we have full control over this parameterization that generates our world, we can introduce the shifts in this world, which are then the shifts in our observed data distribution with highest amounts of control. And then the second part of, you can see there are some example screenshots in the bottom of the slide. We will talk about these later, but maybe you can keep them in mind for a second. And then the second part of our contribution in the paper is that we showcase the utility of the simulator in an example investigation of a number of continual learning mechanisms on these varied scenarios that we can now create. So in the next part, I'm going to introduce you a little bit more into this endless continual learning simulator. So as you maybe have seen already or guessed from the images that we saw below, our general implementation is inspired by urban environments, or more precisely by autonomous driving applications. So on the right side, you can see we have a vehicle with a statically attached camera. And this vehicle will be driving on a street of successively placed street segments. Now, in our simulator is basically comprised of two parts that are neatly working together. And the first one is this procedural real-time world generation process. And the second part is this stochastic model. And this stochastic model is actually a parameterized generative model. And it spans the entirety of our scene. So it spans frequencies of occurrence, textures, and appearance of 3D objects. It also spans all the weather conditions, weather dynamics that we see, and it spans the lighting. It even spans some rendering properties of materials that we see in the world, but I'll show more examples on this later. So if you can imagine now, this model can become or is quite big. And no worries, I'm not going to go into detail on this model like step by step, but I will show you a video that illustrates all of this, hopefully a bit better. But still, if you'd like to read up on this, we have detailed all parts of this model in our paper. And once you go through it, it's actually not that complicated, I promise. Okay, so now let's take a look at the video. And for this, I'll quickly switch up my screen. I hope this is working for you guys. So the first thing I'm going to be talking about is this procedural world generation process. So as you can see here, hopefully see here, is that this world is at no time a static map, but it's continually evolving, and it doesn't even have a real static state. So we can see that as our camera vehicle is progressing, street segments that do no longer add to the scene are removed, and instead new segments are sampled at the end of our street track where it's continued and where the vehicle will drive. And this has some neat properties because at all time we have a limited basically a limited load for our render process, and because we're consistently cleaning up and renewing this world, we have a handle or a hook where we can adjust the sampling for these tiles. So next up, we're going to see how this looks from the camera perspective of the car. And then we're going to see a number of shifts that are going to happen. I'll explain them. But while we see all the neat little annotation types that we basically get for free, let me tell you that this entire track that we're now going to see is taken in one go. So this just to highlight that this thing is really running constantly and continuously. So the first shift that we just witnessed is that we basically adjusted the sampling probabilities for our scene objects, except for buildings and of course the street itself, which we always need. So there are no more cars, no more streets, no more cars, no more trees. And then we're able, after a short period of time, for example, this may be longer in videos that you'd create, but to showcase this, here we then added basically back just not all objects, but most of them, so cars, people, and street lamps. And now we're also adding back trees. So the next thing we're going to look at is a manipulation of the environment, which means lighting and weather situations. So the first thing you noticed is we changed the lighting a lot by switching the time up to 7 a.m. This basically changed the direction from which the lighting is coming. We can also separately adjust the intensity of the lighting. And now we're going to switch over to like a noon time. And of course, again, this is sped up, but this should be a rather simple example for a gradual shift that could be happening. And it's a shift that you will experience basically every day. Now this gradual shift to rain, I just noticed I kind of messed it up. So also these drops on your screen, they should appear slowly, and they do. I just didn't set the parameter right. So we can switch up the weather system, and here we see, first see this coming up of rain, and we see how the clouds actually block sunlight. And then closely we'll see the next shift. Which is going to be an abrupt one to a snowing environment. And finally, we arrive at our clear day. So for the next shift, there's actually going to be happening a lot. We're now looking at shifts that happen to the rendered materials. And this may not be directly something that you think of when you think about continual learning, but this can have some nice properties to look at. So the first thing that I want to explain here is we have basically three properties. These are kind of the standard properties of physically based materials or physically rendered materials, which are their color, then some reflectance properties, and then some additional surface normals. And we can default them to specific values. So what you saw here is that we basically took away the metallicity, or we defaulted the metallicity of our car here. And the next thing that you will see in the distance here is that we basically also don't allow, or we defaulted the color and we defaulted the normals. And this leaves you with basically this gray flat world that you have. And this may be something to look at shifts where you can basically disentangle the shape of objects versus the texture of objects. And this may be something that will eventually can turn out to be a great thing in continual learning. Now here, just for purpose of example, we put back the metallicity of the car, though still we have no color. And then, of course, we could add all the color back to the scene, but I do not think that we're going to do this here, but we'll end the video here. So going back to the presentation, because always when I show these videos, I feel a bit like advertising this. So the last thing that's actually missing for the advertisement is that this thing is available as a standalone executable application. And also the data sets that we generated from this are available, and also the source code. But we'll see this slide again later. I just want to mention it at this point. So the last thing that's kind of missing through understanding this simulation like initially, is when and how to introduce shift into this world. So as I touched on earlier, we are parameterizing the underlying generative model. So what you will basically do is in your first step, you define a first set of parameters that we'll start off with. And then you will have your street segments that are sampled based on this on these generative factors, based on this parameterized stochastic process. So on the left side, we can see a sketch of how this would be laid out. And all of these areas that you can see, these are kind of priors that we imposed basically only on where objects should be placed. And these basically just prevent to cars spawning on top of some buildings or trees spawning in the middle of the road, because this is not something that we want. But everything else is then going to be populated at real time based on the parameters that you set. Then the scene is going to be run for a number of segments. And you can, of course, say how many segments you would like to have this. You can also say how gradual then your shift should be for the next set of parameters that's going to be loaded. And then these tiles or street segments that will then spawn after that point will follow this particular set of parameters. And how will you do this? Currently, the interface is a JSON file. And here, this is just some examples, and you can see you have all these parameters, and you can you will type in your numbers, and then you have your overview of what's going to happen and how it's going to happen, and then you can render your sequence. And this will be then this continuous and consistent data stream that inherently encompasses all this knowledge about the shifts that you're going to observe in the data distribution that you have just declared. So the next thing I'm going to be talking about is the initial investigation of continual learning methods that we used, that we did based on this this simulator. And the first thing that I felt I need to explain is a lot of the time now I've talked about how we can have all of these nice annotations for semantic segmentations, how we can have temporally consistent data, and how we can do all of this new stuff where there was previously no data. But for our experimentation, we stick to image patch classification as well. And this has two reasons mainly. And the first one was we wanted to introduce this simulator, and if we then also moved basically the setup that we did, then it would be kind of hard for the community, or we felt it would be hard for the community, which is you, to follow what's actually new, what has changed, and to relate this back to previous work. And the second thing is that quite early on in our experimentation, we noticed that, we found that image patch classification actually poses a significant challenge. So we stuck to that. And wanted to show this outcome in this setup. So what we here did to get these bounding boxes or to get our image patches is we took our pixel-wise annotation, for which we have for each actor individually or for each object. And from this, we got this nice type bounding boxes, which we then dropped out of the image, warped into 64 by 64 image patches, which is just a convenient thing to do for all of these models that we want to use for all of these networks. And one more thing to notice here is that we only allow minor overlappings of classes because we didn't want to have a multi-class classification setup. So these are the three example setups that we chose. The first one is the classic incremental class setup, where we manipulated the appearance of objects in such a way that we see them in the sequence one after another and each in isolation, as we know it. And then we have two more setups, and these both involve gradual shifts. The first one is this sequence of decreasing lighting. So in each subsequence of our generated video, the lighting was decreased by half of its luminosity. And because this is a log curve, you see these lux values. And then the second sequence is based on weather dynamics. So we first had a sunny day started off, and then we had fog wave rain. And so the difference between these two is, even though they're both gradual shifts, that in lighting, all of this shift is basically induced by one causal factor. And in the weather scenarios, we have a number of factors that come in. So we wanted to investigate this. And these are our results. And I will guide you through this. So the first thing, if you look into the legend, we investigated a number of regularization-based methods, learning without forgetting, synaptic intelligence, elastic weight consolidation, and kind of intermediate gradient episodic memory. And then we used two more rehearsal methods, which is replay and the OCD DAE by Martin Mund. Also, we kind of try to rebound our errors that we expect with an upper bound, which is basically the classic neural network that you have that has access to all data at once and thus should not show any catastrophic forgetting at all. And then we have a naive approach that doesn't use any kind of continual learning mechanism, which shows or should show maximum catastrophic forgetting. Now, when we look at the individual graphs, we can see the overreaching results that there are basically two factions of curves. We have this one faction that is at the very top, and then we have one faction after a tiny gap, and they're also kind of cluttered there. So these curves at the top, the one at the very top that's always stayed close to 98, 99%, this is our upper bound. And then close to it are the rehearsal methods. And then after the gap, we see a lot of we basically see the regularization methods. And for the setup of incremental tasks, incremental classes in tasks, we can still see that basically all of these kind of tend to kick above the naive approach. But if we then look into the scenarios with gradual change, we sometimes see that these approaches stay behind a naive approach, and this was quite interesting. So even though you have something like a task where merely the lighting changes, and you would think that if you regularize your representations, it's still not guaranteed that it's going to work. So that was kind of the main takeaway that we had from these investigations. So lastly, let me talk briefly about prospects. There are a number of things that we'd love to see that people use our simulator for, and we have seen them throughout the talk already. So the first thing would be a transfer to semantic, to different annotation tasks. For example, semantic segmentation, depth estimation, normal estimation. And especially for semantic segmentation, there could be also something not only adding new classes, but maybe also adding more labels or adding more detailed labels that at first you have only object category labels, and then you have for individual objects something in that direction. Then another thing that I've already talked about is this texture versus shape bias and this disentanglement challenge, which could really help continual learning, or may help continual learning at some point. And then, of course, these are all kind of hard to represent in images, but we can now also look at problems of task discovery. So if you have a really gradual change, at what point does your system actually pick up, okay, this is new, I need to incorporate this new information to keep up my performance. We could also look at learning from rare occurrences, where, for example, you have certain kinds of cars only appear for a certain amount of time and then they're gone again, or same for buildings or for any object, basically, or rare conditions in weather, and how does your system act on that? And how long does it take before it has completely forgotten the scenario? And then, of course, by the streaming nature of our data, everything that's connected to online learning and temporary consistency. And so, we hope that we can offer a rich set of interesting open questions to be explored. So finally, in summary, what have we seen? What have I presented? We have seen that, or we have introduced to you a new basically dataset generator based on 3D graphics that creates highly customizable video streams where you have detailed control on the distributions and the distribution shifts. Then we have showcased how one could use the simulator for investigation of continual learning. And we have seen that some continual learning methods are less generally applicable as we would hope they were. And then we have finally outlined some future work that we hope will thrive on this simulator. So here again, the download links for the simulator, for the datasets, and for the source code. And thank you for your attention. And if there are any questions, I hope I can answer them.
Thank you very much, Tim, for your great presentation. So before moving to the questions from the audience, let me just say that I really liked, if I had to pick something from this paper, I really liked, of course, the benchmark, but especially I like the gradual shift approach, which has been studied in the paper, because I don't see very often this kind of experimental setup, while in the real world, I mean, it's kind of common to have a gradual shift instead of a drastic one. And I was very impressed by the fact that many continual learning strategies that today's are, well, maybe not the state of the art, but they are effective, generally considered as effective strategies, completely fail in the gradual shift scenario. So I think this really questions our way of evaluating continual learning strategies, also with respect to the scenarios we have, because of course when you have a really easy to set up scenario, it's very easy to use. So we all tend to use it maybe too much with respect to the alternatives we may have around. But this was just really a personal note. As a question, I was curious about the effort it takes to build the actual simulator. It was mainly a software engineering effort, so to put things together and make the stuff work, or do you have also to work a lot on the generative model, like the performance, the quality of the generated images? Because I can see that they are very high quality, I think, right?
Yeah, this is what so yeah, of course there's a lot of engineering going on there, and to because I had the time in master thesis to really do this, it turned out this way. But I have to say there are two ingredients to this, basically. The first one is I've been using Unreal Engine, and Unreal Engine by default gives you this kind of quality in your images if you have the appropriate assets that can actually, that have this, that incorporate this physics-based rendering process and so on and so forth. But luckily, as we move on, these assets become available more and more, and that's nice. And then the second thing is the endless procedural process that you may know from endless runner games. And yeah, this always kind of limits. There's an absolute maximum of stuff that can happen in your world at one point in time, and you can limit this. So yeah, we don't have to worry about a giant map where we have to query and index into a large arrays of objects, but we always have this limited amount of stuff that's going on. And then the work on the generative model itself. Of course, it was to find the right things that you want to add that are not going out of way to implement. That was kind of a thing, but mostly I would say mostly it's engineering at this point.
Yeah, I see. And as a future work, are you planning maybe to include? I don't know if it is even possible to do that in this benchmark, but are you planning maybe to introduce reinforcement learning facilities into that? Because I think it will be quite nice.
Yes. Also, with respect to this task shifting, even if it's not fully reinforcement learning, to have a hook into the engine where you can say, okay, not after a certain amount of time or a certain amount of tiles, but now I want to shift. Now I want to shift back. This interface, this is definitely something that is doable. but I'm currently working on this alone. So I have limited time and resources to implement this, but it would be great. And we have seen there are papers who do similar things with driving applications especially. So yeah, that would be great to merge reinforcement learning and continual learning. Yes. Yeah, if I have the time, I will.
Yeah, time is a very is a problem, let's say, shared by most of us, I think. But yes, it would be great to see some reinforcement learning tasks in this scenario. It really seems adapt to this kind of stuff.
I think maybe if I can just briefly add on to this.
Please, Martin.
I think this is a really cool idea especially because we've used Unreal Engine. There's some really nice tools. So right now our car basically has a static camera and just drives like through the world like automatically. So it cannot fail because it's basically on a rail. But you could equip this with an actual agent instead, and then have the exact same things that we simulate. And hopefully, when you switch terrain, etc., your reinforcement learning agent is not failing, right? And then I guess there was a question. Maybe I can just quickly answer this from Himati Hamed, who's asked about samples for evaluation. So what we've actually done is we've basically generated 2 tracks. So we've just So just like run the simulator once, and then for a test track, just run the simulator again.
With a different.
So because it's, yeah, exactly. So it's slightly different, and like because it's stochastic, it's not exactly the same. So it's kind of a test set where you know it's still in distribution in that sense, but it's not like you're not just checking overfitting.
Yes. So thank you for answering also the question. Is there any other question or comment from the audience? Feel free also to unmute yourself if you want.
Is it possible to expand the simulator to add new classes? And how easy is it?
Yeah. So this is an important point. In general, saying for me, it's quite easy. I've just added street signs, for example, because this is something that we're just in our working group, there's an interest in that. But as I said, these assets are kind of the breaking point of this thing. And you're not really able to share them. Even though they're free, they're typically, the license is typically limited to you. So just downloading the source code and adding this one object or this number of objects that you want to have, and then run the simulation. This is something that I've been working on currently quite a lot, because to streamlining this process, this is not that easy. And if you see something like Carla, they have great ways to come around this by just adding these maps, and then you download this map, and then everything's fine. But we're working here kind of with asset packages and stuff, so I've not come around this problem. So in general, if it's just a specific add-on a specific object, maybe I could include it, but otherwise it may be a bit of a hassle actually, just to be truthful at this point.
But also, maybe if I can add again, also keep in mind that the way the sampling process, for example, is implemented, like once you have basically an object category in there, you can just drop in like other sort of variants of this
yes, sure.
Like street sign and so on, and it just you don't actually go in like in a classic simulator where you just have to place everything by hand. But it's like if a category exists, it's actually rather easy to just include like variants of it and so on.
Let's say a gradual new classes protocol, which classes are similar to the others once introduced. Okay, I think this answers the questions by Antonio. Any other comment? Okay, if not, let's thank again Tim, of course, for the amazing presentation. Remember to share this talk on YouTube with your family. I'm sure they will appreciate it. Remember everybody to subscribe. We have a YouTube channel which is becoming quite active. And yeah, thank again team for the presentation, and I'll see you all for the next Continual AI seminar, which is of course next Thursday. Thank you
so much.
And bye-bye.
Bye.